All right. I'm gonna do an extra Python lab for those of you who don't have access to Abacus, or if you are just interested. I'm gonna do heat transfer in 1D. We've done that already for the steady state. So the one that I wanna show is the transient heat transfer problem in 1D. So if you recap the steady state problem, that was ddx area times conductivity dtdx plus s equals 0 on some part of the real line, so omega is just a part of the real line, with boundary conditions T equals T bar on part of the boundary which has temperature boundary conditions, and Qn equals minus K dt dx dot n equals Q bar on gamma Q. I'm still using the notation omega and gamma, but here it's really a piece of the real line. So gamma is just either one of the ends. So for example, let's say that I fix the temperature at one end and I have a flux at the other end, and then the rest of the domain would be omega. But I'm just using the same notation that I've been using for 2D, but in 1D, yeah, boundaries are just the ends of the bar, and omega is just part of the line. So this is a steady state problem, and the way it's gonna change for the transient problem is that instead of making it equal to 0, we're gonna introduce the rate of change of the temperature. So everything is gonna look more or less the same. But I am going to say here, this is the rate of change of temperature with respect to time. That's the only difference. But that's going to have some relatively big consequences. We'll see in just a sec. So we have, this is the strong form. So we want to turn this into the weak form. So to turn this into a weak form, we do the same thing that we do every time. Integrate over the domain and multiply by this function. So this is going to be omega times, and then let's assume that ak is constant. So I'm just going to have dt dx square plus s minus dt d time equals 0. So multiply it by omega, integrate over the domain, and then do integration by parts. And I'm gonna end up with minus omega, and then I'm gonna skip a few steps, but hopefully if you go back to the previous lectures, you'll be able to see where this is coming from. So this is gonna be minus omega q bar in gamma q, and then plus omega s d omega. I should probably add a d omega right here, and then minus integral of omega dt t d omega equals 0. So I did integration by parts actually, and use natural boundary condition because I already substituted this q bar right here, so I already used the natural boundary condition. So that is pretty much the weak form that I have. Now this is a problem that changes in time. So now I need to find the temperature, but the temperature will change over time. So now I not only need the essential and natural boundary conditions, but I also need an initial condition, right? So I will need, so now the temperature is a function of x, but also a function of time. So I need an initial condition. In addition to the boundary conditions. And then I'm gonna use that initial condition and this weak form to obtain the temperature at subsequent time steps. So in order to do that, I'm gonna introduce now not only an initial condition, but also discretization of the time derivative. So this dt, let me put it in red. That one I need to discretize. So, and I don't know if you have done this before, but one way, for example, of discretizing would be, the simplest way would be the temperature at the next time step. So at time, t plus delta t minus the temperature at some time t over some time step. Here I'm just gonna adjust notation. So I'm just gonna call this t minus, and I'm gonna call this ti over delta t. So ti is basically temperature field at some time step I, right? So that would be this t of x, so we're all x, but for some time, and I'm gonna call it ti, so some time step, and then this t without the subscript, I'm gonna call that the temperature at the next time step. So temperature field at next time step. So I plus 1, so that will be the temperature over x for ti plus delta t. That's just for notation. It's just gonna make it easier when I plug that in. So if I plug this into the weak form, let me copy this. What I'm gonna end up with is instead of this time derivative, this is gonna be substituted by temperature minus the temperature at the previous time step over the time step. And so basically my problem is now, so this looks very similar to the steady state heat transfer problem, except for this extra term right here. And so my problem is going to be find the temperature. Obviously I'm going to define some space. I want temperatures, which are C0 over omega, so the piece of the real line, with the temperature satisfying the temperature boundary conditions, right? And then also I want given, right? So I want the temperature at the next time step given the temperature at the previous time step. So I assume that I already know the temperature at the previous time step and I know the essential boundary conditions. So knowing those two, I need to find the temperature at the next time step such that this is true I made a mistake. Such that this is true for all W in some space B. Again, I only need W equals 0 on gamma, and I should have done this better. So this is on gamma T, on gamma T. That's it. That's what I want. I want the temperature at the next time step that is C0 continuous, that satisfies the essential boundary conditions, and assuming that I know the temperature at the previous time step, then I need to solve this equation for all W with W equals 0 on the essential boundary condition. And I'll change the color here because the one thing that I want to point out is what is the unknown in this equation that I need to solve. The unknown is actually this temperature field, which appears here and appears here. And that is different from what we have done in the past. So in the past, the heat transfer problem, the steady state, has everything up to here. So you only get the derivative of the temperature, and that's it. And here, we get also this temperature right here. And that's going to have some consequences for the system of equations that we are going to get. So if you remember, what we did for the steady state was after we had this point, we introduced the discretization of the shape functions, and that led to the stiffness matrix and the force vectors. So I'm going to do that. So this is sort of the problem, the statement of the problem. And then I'm going to skip some steps directly into the stiffness matrix and the force vectors. So I'm just going to rearrange this a little bit. I'm going to multiply everything by -1, and I'm going to also, I'm not going to do, I was going to do another thing, but let me just multiply by -1. So here I have the W dx, the T dx. So that one, let me keep like that. Then I'm going to move this, I'm going to split this term, and then I'm going to put it here. So this is going to be plus omega T over delta T. And then I'm going to have all the other force terms. So I'm going to have plus W Q bar on gamma Q. I'm going to have minus integral of omega WS d omega. And then I'm going to have this last term, so that will be minus omega Ti over delta T d omega equals 0. It's the same thing, I just rearranged it a little bit. But the one thing that I'm going to skip is the introduction of the discretization. So what I want to say though is that this right here is gonna lead to the standard stiffness matrix, right? So this is gonna lead, once we introduce the discretization of the shape functions, this is gonna give us this product right here. So the weighting functions times the stiffness matrix times the degrees of freedom, and the stiffness matrix is essentially the integral over the element of dn dx. So the entries ij of the stiffness matrix are the product of the derivatives of the shape functions times ak. So this term right here gives me the standard stiffness matrix. so no worries about that. This term right here is new. We haven't seen this type of term before. And when you introduce the discretization of the shape functions, this is gonna give you a new matrix that I'm gonna call the mass matrix. I guess the correct one would be what is this mass matrix? This mass matrix actually are integrals of ni times nj. So note that here we had ak times derivative of w derivative of temperature, and basically what that leads to is that the ak remains there, and then derivative of w ends up being derivative of shape function I, derivative of temperature ends up being shape function of temperature, derivative of shape function j. For this term right here, we have w times t. So no derivatives, and accordingly what you get is integral of shape function times shape function. And then I just took the 1 over delta t outside of the integral. This term right here, I guess I should say, this term right here, that gives you the standard omega e times the force vector q. So I'm not gonna write that out. This term right here also gives you omega e times the force term due to the source. I'm not gonna write it out. And this term right here is also different. So this one will give you omega times, and let me just take the delta t outside. So it's gonna be 1 over delta t omega times, and then some extra force vector. I'm gonna call it fe0. Or fei, I should probably change the notation, fei. And that just means the contribution from the temperature at the previous time step that I need to add for the current time step. And that fe is gonna be, I actually don't like, maybe I should say ti. So that fti is going to be the integral. You can see here that it's just going to be integral of shape function times ti. I don't like the I. This might be a little bit confusing. So yeah, I don't like this I because it's going to be confusing. Let me just call it T naught, but it's the previous time step. But I guess what I want to, the I should be the index of the shape function. So these are new. Actually, this is the same as before. But the new ones are going to be this one and this one. So if you substitute this, what you'll see is that I'm gonna get, at the end of the day, I'm gonna get the stiffness matrix times the D, plus now I'm gonna get this 1 over delta T, the mass matrix times the D, plus the force vector due to the fluxes, minus the force vector due to the source, minus this force vector, I'm gonna call it F naught, which is basically the contribution from the previous time step, equals 0. So if we rearrange this a little bit, I'm gonna end up with 1 over delta T mass matrix plus stiffness matrix times D equals minus FQ plus Fs plus F naught. And this is the system of equations that I need to solve. And again, if you compare to the steady state heat transfer, what are the differences? The differences is this 1 over delta T times this mass matrix and this term right here. Those are the only difference. This F naught term, which is the integral of the shape functions times the previous temperature. So the temperature of the previous time step. Those are the two extra vectors and matrices that we need to account for. The other ones are the same. So this K is the same, FQ is the same, Fs is the same as before. This D is the same, it's just the vector with the temperatures at the next time step. So again, really the only things that changed here are this mass matrix and the F naught vector, which is basically the temperature from the previous time.